All right, we're going to start on integration of rational functions by partial fractions. So essentially this is, let's do some fun algebra to get something into a form, a rational function into a form that we can integrate it. So if you look at this, we can see that we have, we essentially have a rational function that we're going to express as the sum of two different rational functions. All right, so we're going to split this up into something that then we will start to make into a simpler form that will allow us to integrate it more easily. All right, and so if we were to integrate this one, well, let's just go through and look at this. We can look at this and we can say, all right, we know that 5x minus 3 over x squared minus 2x minus 3 equals 2 over x plus 1 plus 3 over x minus 3. And you know this because I'm telling you it is. In a bit, we will figure out how to find that. In other words, we will start with this and figure out how to come up with that. But for right now, trust me, just so we can see the benefit of doing this. All right, this is going to work out nicely for us. So essentially what we're going to want to do, well, I mean, I guess you're trusting me on this, that this becomes something we can actually then integrate, which shouldn't be too hard. This should be 2 ln x plus 1 plus 3 ln, oops, that's more curvy, straight line, x minus 3 plus c, right? And we could do that one pretty easily. If you don't like to just write that one straight out, you could do u equals x plus 1 and do u substitution, and you'll end up with that natural log of x plus 1 because you'll be doing 2 over u. So it'll be the natural log of u, and then you just swap it back. So, and you can do the same thing for the 3 over x minus 3. You make u equal x minus 3 and do it if you don't like doing that in one step, okay? But there you go. That's something that is very integratable. Whereas this first form, the 5x minus 3 over x squared minus 2x minus 3, is not. Yeah. Yes. Yep. No, thank you. That's okay. I often forget. So anyway, how in the world do we start to come up with that? Well, we do this, if we look at this one, by starting with a 5x minus 3. In other words, how do we get to the partial fractions here? And then we have the x squared minus 2x minus 3. We can actually factor that, right? So this actually will become x plus 1, x minus 3. Everybody agree with that? Okay. And so what I want to do is say, all right, this is going to be some sort of something over x plus 1 plus something over x minus 3. Do we agree that that would possibly be the case there, right? We could then, if we wanted to combine a plus b there, you know, those two fractions together, we'd say the common denominator is x plus 1 times x minus 3, right? And you'd have like a x minus 3 times, you know, or plus b times x plus 1, right? So if you made a common denominator and you grouped them together, so we can separate them like that. What I then can do is, you know, I can combine the fractions together, or you can think of it as I'm just going to multiply everything by x plus 1 times x minus 3. I'm going to multiply that through by the whole thing, okay, both sides. What that will do is give me just 5x minus 3 on this left side. And over here, when I do x plus 1 times x minus 3 times that first fraction, a over x plus 1, the x plus 1's cancel, and I'm left with a times x minus 3. And then when I multiply it by the second fraction, the x minus 3's will cancel, and I'll be left with b times x plus 1. So I just multiplied by the denominator, essentially, of what was on the left. Okay? Now I need to figure out what these things are. So I'm going to go ahead and distribute. This will be ax minus 3a plus bx plus b, just like that. Then I'm going to group. All right, so what did we do first? We multiplied by the denominator. That's DNOM. And then we distributed. Now, well, actually, that's multiplied by the denominator right there. Then I distributed here. Now I'm going to group 5x minus 3, group all my like terms in the powers of x. So I have an ax and a bx. That can be a x times a plus b. And then I have a 3a and a b. So a minus 3a plus b. Okay. Now, if we look at this, we should see that we have, in the left side, we have 5x minus 3. On the right side, we have something times x plus some other constant, right? So what we can do is say, look, we can match this up. We have 5 times x over here. Here we have something times x. Over here, we have minus 3. Over here, we have minus 3a plus b. So what we can do is actually combine these together, and we can say that a plus b has to equal 5, and negative 3a plus b has to equal negative 3. Now we have 2 equations with 2 unknowns. And we need to know what a and b are, right? So we take these 2 things and we solve them. Solve a and b, okay? And a nice easy way would be just to subtract the second one from the first one. So you could do whatever you want. You could solve for a and then substitute in the other one. You could do the matrix versions of these, whatever you need to do to solve for these. Right here, I have a plus b and a plus b. So immediately it just looks easy to me just to subtract the 2, right? Because that'll cancel out b. So this will be a plus b equals 5 minus negative 3a plus b equals negative 3. Okay? And so I end up with a minus negative 3a. That's a 4a. I have b minus b. That's a 0. And I have 5 minus negative 3. That's an 8. So there we go. A is equal to 2. After I get a equals 2, yeah. Are you raising your hand or?
Yeah, wouldn't it be a minus, oh, okay, no, I confused myself.
It's okay. All right. So now we can solve this for b. Pick either one you want. I'll go with a plus b equals 5, so 2 plus b. So here's a. Solve for b. 2 plus b equals 5, which means b equals 3. Okay? Which, if we come back up here to what we had right up here, that gives us, what, 2 over x plus 1 plus 3 over x minus 3, which is what I said it was at the very beginning.
Can we keep b and 8 and do 3 over x plus 1 plus 2 over x minus 3?
No. No. Try it and see. It won't work out. It won't work out. When you combine those into one fraction, the coefficients will all be wrong. Right? Because what you'd end up doing is you'd be doing like 2. You'd end up putting a 2 right here, right? A 2 right here, and the 3 over here, which is going to change your coefficients. Now, maybe in some cases you might get lucky and it works, but in general, no. It'll change your coefficients. All right. Any questions on that? Uh-oh, what did I walk into today? Listen, don't worry. It gets worse.
Yes.
Just stay with me here. So let's take a look here. What? What happened? Oh, okay. So essentially what we have here are rational, oops, I probably have to, rational function where we'll have an f of x over a g of x, just like that. All right, so this method is going to depend on two things. One, proper fraction. Okay, what we mean here is the degree of f has to be less than the degree of g. If degree of f is greater than the degree of g, then divide. Do your long division or synthetic division or whatever. I tend to prefer just to do long division. Never remember if I remember synthetic division correctly, and it's kind of like only works in certain cases, you know, special cases and all that kind of stuff. So I just stick with long division. All right. And second, g of x is factorable as linear and or irreducible quadratics. Okay. So if those two things are good, we're good to go. And we can start doing this. So how do we do this for just general cases? Well, that's what we got right here. In fact, 1 and 2, you may or may not, you may be just picking between 1 or 2 or doing both of them. So let's look at 1. Let x minus r be a linear factor of g of x. That's the denominator. Suppose that x minus r to the m is the highest power of x minus r that divides g of x. Then, to this factor, assign the sum of the m partial fractions. So what we mean by that is, if we have something like an example here, if I have x over x plus 1 squared, you know, I can factor it down to that. Then I'll have a over x plus 1 plus b over x plus 1 squared. And so if it had been x over x plus 1 to the 5th, I would have had a over x plus 1, b over x plus 2, x plus 1 squared, c over x plus 1 cubed, so on and so all the way until I get to the 5th. However many of them there are. So it's not just x plus 1, x plus 1, x plus 1. It's x plus 1, x plus 1 squared, x plus 1 cubed, x plus 1 to the 4th, x plus 1 to the 5th. And you go on like that. And so you break them down that way. So factor it out, take that power, and that's how many times you need it to show up. Okay? In part 2, step 2, let x squared plus px plus q be an irreducible quadratic factor of g of x. So we can't get this one down to like what we have in step 1, right? We have to leave it as that. So that x squared plus px plus q has no real roots. Okay? If it's real roots, then we can break it down further, and you should. Suppose that x squared plus px plus q to the n is the highest power of this factor that divides g of x. Then to this factor, assign the sum of the n partial fractions. And see the form that they take there. bx, b1, x plus c1 over x squared plus px plus q. And then, you know, b2x plus c2 over that. So, so you go through and get that. Now, this is something like what do we have here? I put this little example. X over x squared plus 1 squared, right? You're going to have ax plus b, that's a b, over x squared plus 1, and then plus cx plus d over x squared plus 1 squared. I didn't squish that in there very well. Then you keep going down. So if that was a cubed in the denominator on the left there, then we'd have another term, ex plus f over that, you know, and you just keep going. Yeah. Yeah. Yeah, they're just arbitrary things. They just have to be different. B1 has no relation to B2. Okay? Just like up there, A1 has no relation to A2 in step 1. I just did A and B. You can keep track of it through subscripts if you'd rather. I mean, especially if they get very big, you kind of start to run out of numbers. Or not out of numbers, out of letters. You don't really run out of numbers. It's up to you. You could, I mean, if you wanted, make this, you know, equals smiley face x plus squiggly line or something over x squared plus 1. I mean, I don't really care, right? Sunshine x plus, I don't know, squid. There you go. Over x squared plus 1 squared. It doesn't really matter. It's all I'm trying to say here. Okay, you can put whatever you want. That's pretty. You look at that and you think squid, don't you?
No, I'm not thinking like a person's
No, you think squid.
Yeah, it looks like those,
Pretty sure it was a squid. Anyway, art lesson over for how to draw beautiful little simple squids that obviously look like squids. And that's the brilliance of it, is that it's so simplistic yet still very much conveyed squid. You break it down into its simplest parts. That's the thing. Yeah, I've got that down. And then part 3, set the original fraction equal to the sum of all these partial fractions. Clear the resulting equation of fractions and arrange the terms in decreasing powers x, which is what we did on the last page. We multiplied both sides, we got rid of all the fractions, we grouped everything together in decreasing orders of fraction, equate the coefficients with the corresponding powers of x, and solve for them. Okay? So in this, it's sometimes a lot simpler than it is in practice, which is not usually saying much because this isn't super simple to say. You know what I mean? Like, if you look through this isn't like super simple necessarily, but it's simpler here than it can be in practice. Like when you start doing these, sometimes it can get a bit tricky. So take your time, go step by step, make sure you're remembering your powers, make sure you're doing everything the way you are supposed to. So let's go ahead and go right here. We have this one that's already nice and divided up for us, x minus 1, x plus 1, x plus 3. So go ahead and I want you to break this up into some partial fractions like we just did. You're going to have 3. You'll have an a, a b, and a c. So nothing complicated. No ax plus c, you know, just a over something, b over something, plus c over something. So I'll pause this for a minute. See if you can set it up. What does it equal? What is our partial fraction? And then start solving for a, b, and c. Here's this one all worked out. So hopefully you're able to get it to turn out just like that one. So zoom in if you want to pause it and see this first part where I just broke it up and then started getting in the same form and isolating all the powers of x, setting them equal to each other. Just went through and did some combinations of those 3 equations I came up with there to eliminate and solve for a, b, and c. I actually solved for b first, then a, then c. Then I plug them in, divide this up into the partial fractions. It becomes a pretty simple integral after that. Just some natural logs with those coefficients out in front. All right. Let's yeah. I did the integral.
I know, but we just did that in that form,
What form?
like the natural absolute.
I don't know any other form to put that in.
Oh, do you mean like solving? Like,
I mean, it's indefinite, so yeah, there's no plugging in or anything like that. It just we're done right there. If it was a definite integral, you'd have to plug stuff in. Yeah. Or you want to try and like combine all the natural logs into something, into like one natural log. No, you can leave it like that. Because I already used a C. I used a C. Right, get that C up here. C. Okay. Let's take a look at this one. I'm going to let you have this one all to your own. Okay? Next class, go through that. So for this one, actually, let's get you started on these two. Just real quick, what is this one going to look like? When we start breaking this 6x plus 7 over x plus 2 squared, what's this going to equal?
Over x plus 2 plus b over x plus 2 squared.
There you go. Right? And it has to be that way because if we didn't have all the different powers, if we just stopped with x plus 2, I mean, the common denominator is x plus 2 squared. So we need all the possible versions that could give us that common denominator. So that's an x plus 1 to the first and an x plus 1 squared, not an x plus 1 to the third or anything like that. That's too big. All right. That may turn out that like a is 0 or something like that in some case where, you know, but all we know is those are possible. We need those coefficients. Okay. So that gets you started on that one. And then this one, take a look here. What do we do here?
A plus B plus C plus D.
Factor out first, bottom.
So you want to factor the bottom first? I'm going to say no. Nope, not first. Say that again?
Oh, we do down division first.
We got to divide first.
Oh.
The degree of the numerator here, degree of f is greater than degree of g. So divide first. And then I'll give you a little hint. You ready? After you do this division and you split it up, you're gonna end up with a remainder. And you'll have something that works out nice, and then you'll have a remainder over here. So you'll have some polynomial and then a remainder. So you'll still have a fraction. When you get that, I want you to go back and look at the very first page of these notes. Okay? And then you'll say, thanks for pointing that out to me. Because otherwise you're redoing something. So just when you get that, you should end up with what we did on the very first page is what I'm saying. So if you don't, then you've done the division wrong. Okay? Go through, do that, and it should turn out nice for you, okay? All right. Sorry, Patrick, I just saw your answer. Nope, we gotta divide first. Divide first. Okay, so try that. Divide the numerator by the denominator. Okay, and I'll stop recording there.